Hello guys, I welcome you to our channel. This is your strength of material. Strength of material. Strength of material. Strength of material is very important subject in your civil engineering. आपका सॉम वीक है तो आपको बाकी सब्जेक्ट्स में प्रॉब्लम करेगा, जैसे स्ट्रक्चरल एनालिसिस में आरसीसी और डिजाइन ऑफ स्टील स्ट्रक्चर्स. SOM is very important for your civil engineering. Our main concern in strength of material is to study the behavior of materials when they are subjected to forces and moments. Suppose a body is here, we apply forces and moments. We want to check the behavior. This is to study the behavior of materials. We would this is our concern here. Each structural member is made up of material, which could be rigid body material, or it can be deformable material. If you have a rigid body here, concept rigid body material. Suppose this is your body, and at two molecules A and B are at a distance of L. Now you apply forces and moments on the body. After the application of forces and moments, let's say the length between A and B is now L dash. If L dash is equal to L, or we can say it is approximately L, then we would say the body is rigid body. On the other hand, same body, A and B at a distance L. After that, after the forces and moments you have applied, after L dash, if L dash is not equal to L, which implies that the body has been deformed from its initial position, initial shape, so we say body is deformable body. It has undergone deformations. No, so what is the deformation? Deformation is change in shape, size, geometry. अगर बॉडी की शेप चेंज होगी, साइज या जियोमेट्री चेंज होगी ऑन द एप्लीकेशन ऑफ फोर्सेस एंड मोमेंट्स, we'd say body is deformable body. Now we have a concept of if you use engineering science, we have divided into two main branches: solid mechanics and fluid mechanics. You have a body here. Now you apply a force, say 100 kilonewton. Now what would happen? After some time t equals 2 seconds, the body has been deformed this way. Suppose the angle made here is phi, and the deformation that's produced here would be same as produced here. Say it's delta 1, phi 1, delta 1 deformation. After time t equals 10 seconds, the deformation and deformations are same, phi 1, delta 1. Now come back again after time equals 20 seconds. आपका phi और delta same है. That means deformations are not varying. Deformations are not varying with time. Now same body, but if it is a fluid, take a fluid body, we say that body is fluid, apply force F. Initially the body would displace, say, delta 1. At time t1, body will displace phi 1 delta 1. But after time, if you come back at time t2, the body would displace this way. Body would displace this way. There will be phi 2 delta 2 phi 1 phi 2. At time t3 phi 3 delta 3. That means with time आपका deformations vary हो रहे हैं. Deformations vary. This is your deformable body. So main strength जो आपका engineering mechanics है, you have studied there. We have used the concept of rigid body in engineering mechanics. It is a simplified analysis, but in the deformable body, we would study strength of material. In that, we would be calculating deformations in terms of slopes and displacements, also stresses, strains, etc. Since the body is deforming, we say the body is deformable body. So coming back to our main topic, this is our stresses and strains. Stresses and strain. What do you think? What is stress and strain? Say you have a body on a frictionless surface. Now you apply a force F. Since there is no restraint on the body पे कोई फोर्स जो है वो अपोज नहीं कर रहा है इसको, इस फोर्स F को कोई अपोज नहीं कर रहा है, तो the body will undergo, we call it as rigid body displacement. Say it would displace with acceleration we have F by m. So there's no stresses developed. Now take same body apply on the same frictionless surface. Now apply force F, but now you use a concept of a support. Say you have support used here, you have applied a support here. Now what would happen to the body? See, in the civil engineering's these free body diagrams are very, very important. These are the heart. Free body diagrams are the heart of civil engineering. So if we want to analyze what would happen to the body, let's take a body like this one. You are applying force F. Now let's say for easy analysis we will say body load is acting through the centroid, and apply the restraint is applying force, restraint force. Here you are applying a force F, and the support is reacting, it is not allowing the deformation to happen. Here delta equals 0, which implies it can't go in horizontal direction. The body won't undergo displacement in horizontal direction, so we say delta equals 0. If the deformation is 0 but you are applying force, it's kind of body getting compressed. By an equivalent opposite force on either side of body. So body is getting compressed. What would happen to the interior material? Molecules would be undergoing compression. What would be the value of R? Firstly, if you apply equilibrium of forces, we say summation of forces in horizontal direction equals 0, which implies taking this as positive, would say F minus R equals 0, F equals R. That means your reacting force is equal to force itself. So if we want to check the body is getting under stress, so body would say no, I don't want to become compressed. So there is an internal tendency to compression, to get compressed, तो body resist करेगी इस compression को. If we apply free body diagram, would say how it would happen. So it is a body, you are applying force F. Suppose इसके कुछ dimensions भी होंगे इस body के. Let's take that as this one. This is your cross section. This way. Suppose body load is acting through the centroid. Okay. ये आपका length L है, breadth, depth. Suppose the force is P now. What would happen? So if we take any cross section, internal cross section, suppose आपने कोई cross section काटा यहाँ पे ऐसे, suppose this is a cross section you have cut. You want to see what is happening on this cross section. If we cut the section here on the body, we would do free body analysis of this section like this. Here force is B, and now here would be some internal force trying to resist the deformation. So from equilibrium we would say your P internal force, जो आपका P internal force है वो that is equal to P. So if you want to say what is stress, stress is like that of pressure. It's load, internal pressure, internal force, resisting force, internal resisting force per unit area. जो आपका एरिया है उसके उस पे जो internal force है that's acting, so that's your stress. A Newton per meter square. That is also Pascal. Okay. So what if we write the definition of stress, we would say stress is the internal resistance against deformations. If we apply a zoom level, we would say, let's take now force that's trying to extend the material. We would say force is in tensile force. You apply force, tensile force. The body will elongate F. Suppose the length is L. After the application of force, the deformations are like this. Body has been displaced, and now the final length has been changed to L plus delta L. Now, if we have a concept of strain, longitudinal strain. What strain? Longitudinal strain. That's equal to change in length upon original length. Change in length is final length L final minus L initial by L initial. आपका final length है L plus delta L minus initial length was L minus L initial was L. So your strain is equal to delta L upon L. So for tensile force, strain would be positive, and for compressive force, strain would be negative. So body, this is your strain concept. You may have studied Hooke's law. Hooke's law. Hooke's law. What's Hooke's law says? Hooke's law says stress is proportional to strain when stress is itself, stress is in proportional limit. Or we can say stress अगर stress का value अगर proportional limit के नीचे है, is below proportional limit, we would say stress is proportional to strain. If you have studied earlier the stress strain curve of steel, stress strain curve, it is somewhat like this one. So in the initial portion, that's linear portion up to A from origin, we say that the slope is constant, and this is what the value, the A is the proportional limit up to which stress is directly proportional to strain. That means the graph is a straight line till A. The assumptions in the Hooke's law is material is isotropic, homogeneous, and linear elastic. We would study further in detail of in the subsequent lecture. So आपका stress is proportional to strain. Then we use to remove the proportionality limit, we introduce a constant. Stress equals E into epsilon. What's E? It's called as Young's modulus of elasticity. Young's modulus of elasticity. Earlier we have studied this one, that you apply force P and you have cross-sectional area A, and the body has been deformed to L plus delta L. Then the strain was delta L upon L, and stress was equals P internal by area cross-section. P internal, we have checked from the equilibrium of forces that P internal is equal to P upon A. Now if we apply, if we deploy these values in this equation, we would see what's the result. Stress is equals P by A. Stress equals P by A into E, and you have epsilon delta L upon L. So if we get the important result, that's delta L equals PL upon AE. So your deformation equals PL upon AE. It has a unit of millimeters, say meter. Okay. Now the stresses, this strain, firstly the strain, that's delta L upon L. It is a fundamental quantity. That is material dependent. That is material dependent. But your stress equals P upon A. It's not material dependent. It's not a fundamental it's not fundamental property of material, but it is a derived concept. So your fundamental property of material is strain. Strain we measure using the concept of electrical resistivity. You use these extensometers on the body. Suppose you have body, you apply those wires on this on the body, then after the application of forces, the wires length change, accordingly the resistivity change. Then from calibration we check the strain value. Okay, now stresses are divided into normal stress and shear stress. Normal stress is the stress acting perpendicular to perpendicular to surface. जैसे आपका बॉडी यहाँ पे है, you have body, then आपने अप्लाई किया tensile force P, then the stress developed on the surface of body was perpendicular to it. Like this was your surface, then the stress was equals P by A. That's acting perpendicular to the surface of the body. This is your normal stress. Second one is your shear stress. Stress acting parallel to surface. Suppose this is your loading. Yeah, this is your member, and this is your loading, some sort of loadings, and then you have a cross section here. You would check the then from the equilibrium you would calculate some internal force on this cross section. We would say suppose the value of this force is V, shear force equals V. We would say the shear stress, we represent it as tau equals shear stress upon area cross sectional, but it is force is parallel to the surface itself. इसमें आपका force was perpendicular, accordingly the stress we calculated was perpendicular to the surface. Here force is itself parallel to the surface, so shear stress is acting parallel to the surface. Normal stresses or further it can be axial stress, it can be bending stress, or it can be bearing stress. As of now, we would be studying axial stress only. That is, when the load is passing through the axis, central axis, then we would calculate the internal force. We would calculate the internal force, sigma axial equals P upon A. As of now, okay. Next one was your shear stress. Shear stress. It can be direct shear stress, or it can be indirect shear stress. The direct shear stress was this one. It was because of the forces, direct action of forces trying to shear the material. Suppose I haven't shown you the section. Suppose because of the loading, some loading was there. Now you got a section somewhere. So here the shear force would be acting like this one. Suppose you have a section. Suppose here in this direction shear is this way, and in this direction shear is this way. It's trying to cut the section. Suppose you cut the paper, you apply force in one side of section, you apply force in this direction, and in the other side you apply opposite to that. Then you try to shear the material. This is your direct shear stress. Indirect shear stress is arise because of many reasons. For example, because of torsion. Torsion, we will be studying it later. Torsion. Now your topic is like what is the topic? Next topic, this is your stress. What is stress? Stress, it is a tensor quantity. Tensor quantity. What's tensor? आपका स्केलर भी है, उसके बाद वेक्टर है. Now third one is your tensor. Tensor. स्केलर में आपका मैग्नीट्यूड ओनली होता है, इसमें वेक्टर में मैग्नीट्यूड प्लस डायरेक्शन. नाउ टेंसर में आपका मैग्नीट्यूड प्लस डायरेक्शन प्लस plane. A plane on which the stress is acting. That's why the stress is a tensor quantity. Suppose if you want to have the stress representation, we write it as tau ij. Tau ij. I represents the plane at which stress is acting. Okay. The plane at which stress is acting, उस plane पे हम outward normal डालेंगे. The direction of outward normal will represent the direction of I, and your J is represents the direction of arrow, like this way or this way. Or we can write tau. Suppose you have a member. You have a member. You take some section anywhere. Let's take somewhere section, a three-dimensional section. It would be like this one. Now let's take reference axis as this one x, this one z, and this one y, and take in this direction x as positive, upward y as positive, in this direction z as positive. This is your z axis, this is your x axis, this is your y axis. Now take any plane and we want to say what is the how do you represent that stress quantity. Suppose इस पे different stresses act कर रहे हैं. Let's take any section. If you want to check the if you say this one, it is a stress 1, we say it is a tau. On this plane it is a tau, on this plane it is a tau, on this plane it is some tau. Okay, we want to see what should be the notation of this tau. See, this plane, it's acting on this plane. इस प्लेन पे ये टाउ एक्ट कर रहा है, तो इसका देखना है टाउ आई जी. हाउ डू यू रिप्रेजेंट दिस टाउ? आई रिप्रेजेंट इज द प्लेन एट विच टाउ इज एक्टिंग. आपका टाउ इस प्लेन पे एक्ट कर रहा है. ये जो प्लेन है, दिस प्लेन, it's this plane. We want to check the I value of I. उस प्लेन के ऊपर आउटवर्ड नॉर्मल डालना है, ठीक है, आउटवर्ड नॉर्मल ऑन दिस प्लेन इटसेल्फ. इस प्लेन पे अगर हम आउटवर्ड नॉर्मल डालेंगे, से दिस वन, दिस इज योर आउटवर्ड नॉर्मल, ऐसे. So it is the direction of x itself, isn't it? It's the direction of x is itself. से थोड़ा सा इसको ऐसे करेंगे. It's the direction of x itself. So you can represent it as tau I was equals, किस डायरेक्शन में है, इसका आउटवर्ड नॉर्मल है x में. Then we want to check the value of this j. J is the direction of arrow. J is the direction of arrow. जो आपका टाउ का डायरेक्शन है, उसका जो itself डायरेक्शन है वही लेना है. इसका डायरेक्शन इज इन द डायरेक्शन ऑफ x. ओके, दिस इज योर टाउ xx. सो इसको रिमूव करेंगे. We can write it as tau xx. Now coming back to this tau, it's acting on this plane. I का वैल्यू है कि इस प्लेन पे outward normal. If we apply outward normal on this plane, it is the direction of y. That means you have a tau y. इसके बाद j is the direction of arrow. J is the direction of arrow. इसका डायरेक्शन, arrow का डायरेक्शन यहाँ पे ऐसे है. It is in the direction of x. ऐसे tau yx. We can write it as tau yx. Now we can write now for this plane also. This tau is acting on this plane. On this plane. Okay. What should be the representation of this tau, of this stress? We would say it is plane पे outward normal डालो, ठीक है. That is the direction of y and tau y. Now j, what is the value of j? Direction of arrow. The direction of arrow is in the direction of minus x. We can write it as tau yx. Tau yx. Similarly, this one is also a tau xx. Let's take some another force. Suppose this one force. This force. Tau. Now I is equal to, the stress is acting on this plane, तो इसके ऊपर outward normal. That means it is tau x. उसके बाद direction of arrow of the stress is in the direction of y. Then your stress becomes tau xy. That's your stress representation. Now उसके बाद आपका sign convention भी है. would represent right also, and sign convention. Sign convention. देखो, in the direction of this x, we write it as positive. Suppose you have this one, we say the value of tau x should be equals, देखो, direction of this x, मतलब आउटवर्ड नॉर्मल का डायरेक्शन पॉजिटिव है, आउटवर्ड नॉर्मल का डायरेक्शन पॉजिटिव एक्सिस है, एक्स एक्सिस में है, और द एंड द डायरेक्शन ऑफ एरो इट्स आल्सो इन द पॉजिटिव डायरेक्शन, दोनों ऐसे जा रहे हैं. दैट मीन्स ओवरऑल द टाउ एक्स एक्सिस इज पॉजिटिव. नाउ चेकिंग फॉर टाउ वाई एक्स. इसका आउटवर्ड नॉर्मल is in the direction of positive y axis. You have positive y and x मतलब कि the direction of arrow is in the direction of positive x. That means your tau yx is also positive. If you want to check the value of tau yx is plane पे outward normal tau yx. The direction of this outward normal is in the direction of minus y, and the direction of the arrow is in the direction of negative minus x. Then the overall negative it becomes overall positive. For this also similarly it will become positive. Now if we want to check for tau xy, इस स्ट्रेस के जो the plane on which this stress is acting, उस पे आउटवर्ड नॉर्मल डालेंगे ऐसे, that is in the direction of positive x, and for the y direction of arrow it is in the direction of positive y, so overall positive stress. Let's take same this element of the body. If we apply the force, let's say I am applying tau in this direction, tau. We want to check the represent it and check the sign of this stress. Say this was your positive x, this was your positive y, and this was your positive z. It is acting on this plane. इस प्लेन पे एक्ट कर रहा है, तो टाउ आई का वैल्यू है कि इस प्लेन पे आउटवर्ड नॉर्मल, दैट इज इन द डायरेक्शन ऑफ पॉजिटिव एक्स. दैट मीन्स जस्ट टाउ एक्स इज पॉजिटिव. उसके बाद टाउ एक्स जे इज द डायरेक्शन ऑफ एरो इटसेल्फ. डायरेक्शन ऑफ एरो इज इन द डायरेक्शन ऑफ नेगेटिव वाई. It is in the direction of negative y. Overall the stress is negative. Okay. Now we have a concept of a very important concept, that's equality of shear stress. Equality of shear stress on two perpendicular planes. Let's take any element. Of the body. Shear stress. For the shear stress, we say for your simplified analysis, we take the case of pure shear. उसका मतलब है कि the element of the body is subjected to only shear stresses. No normal stresses are acting. Okay, pure shear मतलब कि tau only shear stress is acting. Tau acting. Now let's say now some forces would be there, wait, on this plane, and on this plane. Now you have learned the stress representation. इसका वैल्यू जो है वो है टाउ, इसका नॉर्मल डालेंगे, इस प्लेन पे नॉर्मल डालेंगे तो इट इज इन द डायरेक्शन ऑफ एक्स एंड its direction is upwards, so that is your tau xy. Similarly iska now this one you have normal is in the direction of y, and this direction of arrow is in the direction of x, it is your tau yx. Both are positive from sign convention, can check from the above. Let's say we would say what is the value of this this stress now. We know its representation is also tau xy and its representation is tau yx. Now let's say this one is your, we represent it as stress 1, this one also, let's say 2, this one has 3, this one has 4. We want to check the equality of shear stress. What does it mean? Equality of shear stress. Okay, now let's use the concept of force equilibrium. This element dimensions, let's say this is your dx, in the direction of y it is your dy, and in the direction of z it is your dz. Now we can represent this 3D element in 2D as this one. Let's say this one is your force 1, this one is your force 2, this one is your force 3, and this one is your force 4, F4. Dimensions are like this one. Now what's the value of force 1? Force 1 equals this stress tau yx1 into the plane area, the area of this plane, that is equals to dx into dz. The value of force 2 equals, force 2 का value जो है वो है this stress tau xy2 and acting in this plane dz dy. Okay, similarly you have force 3 equals tau yx3 into this plane area on which tau yx3 is acting. This is your dz into dx. Force 4 is your tau xy4 into d, this one, this area is dz into dy. Now let's take force equilibrium. From the free body, from this diagram, if your force F1 is in horizontal direction, that means the other force in the horizontal direction has to be equal to F1 in the opposite direction. So to maintain the equilibrium of forces, else if there is no equilibrium, suppose there is external some force, there would be acceleration of the structure. In the civil engineering, we say that the acceleration should be 0. We want building to be at the position where we have built it. We don't want it to move. So for that we would apply force equilibrium always. Okay, So f1 equals f4. If we f1 equals f4, if we check the f1 and f4 values, we would say f1 and f4 values, that is tau y x1 dx dz equals tau xy wait a minute f3 was your f3 was your tau y x3 d2 dz dx, and f4 was your tau xy dz d4. So this one was your f4, this one is your f3. So you're in the equilibrium of forces, would say f1 equals f3. That then the f3 is equals tau y x3 dz dx. Then your dx dz cancels, which implies tau y x1 equals tau y x3, which implies on the two sides, if here is acting tau xy, tau yx, the stress on this direction would be equals to tau yx. This is just a representation. 1 and 3 are the same thing. We can write it as tau yx. Now to check the value of, now to compare the value of this force 1 and force 2. Now we'd say we want to check the value of force 1. Force 1, force 2. Similarly, force 3 was here, force 4 was here. Now if we apply concept next equilibrium condition, that is the moment equilibrium. Similarly, we don't want the body to rotate, we don't want the structure to rotate, so for that moments should be balanced. Okay, we say, let's take it as O. We say summation of moments at O goes to 0. Now this is your dimension dy, this is your dx. Now your now you have to do the summation of moments around this point. So f1 into dy, force 1 into displacement dy, we'll say. In the we write it clockwise as positive, so it's your positive value, plus f2 dx, but f2 is acting on with respect to this as anti-clockwise, so we would write as minus f2 dx equals 0. So from that, what's the value of f1? Firstly, f1 was equals to tau yx dx dz, tau yx dx dz into dy plus minus f2 का वैल्यू जो है, that's tau xy dz dy, tau xy dz dy into dx equals 0. So your this goes cancel, and your tau yx is equal to tau xy. This is important conclusion. That is, now you write the two statements that you can use for your strength of material. That is shear stress on opposite faces of material, yeah, element are equal in magnitude and opposite in direction. That is this one. We take it as f1, f3. Then it was some sort of tau yx, and it was tau yx into some area. So your then the area was also same. You got tau yx in the direction in this three direction, and in the one direction as same. So we write it shear stress on opposite faces, this one and this one, on opposite faces of element, opposite faces of element, this one and its opposite here. Tau is same, tau with the value of tau is same in the both these faces, but direction is opposed. Second statement was, we can write as shear stresses on adjacent faces. जो adjacent faces थे of element, उनका जो value है same, that magnitude is same, but direction is such that both meet, that's both point towards or away from the intersection of planes. As you can see from this one, you got tau yx equals tau xy. You got this tau yx equals tau xy. You got tau yx equals tau xy, such that their magnitude is same. You have seen the magnitude was same, and the direction is such that both point towards the intersection of planes, or away from both point away from the intersection of planes. Here also you can have tau xy and tau yx same, but both are away from the intersection of this these two planes. इस plane और इस plane का जो intersection है, उससे ये दूर जा रहे हैं इस point पे, और इस वाली intersection पे ये tau xy and tau yx, they are pointing towards each other, towards the intersection. Oh my god. Okay, next topic is your if you write the general stress representation. We know stress is a tensor quantity. If you have three planes, xy plane, sorry, if you have we have three planes, xy plane, yz plane, and zx plane. So from the figure you might have seen, if it was your plane 1, let's say it's your plane xy plane, you have three stress values. One was your tau yx, next one was your tau xy, third one is your tau xx. So each plane has two shear stresses and one normal stress. Normal stress is this one, tau xx. We can write it as also as tau sigma x. So for the three planes we can derive a stress matrix as tau ij stress matrix. Tau ij equals tau xx, tau xy, tau xz, tau y x, tau yy, tau yz, tau zx, tau zy, tau zz. And from here we have seen we can write tau xx as sigma x. Sigma x, this one is corresponding to sigma y, and this one sigma z, and this one is your tau xy, tau xz, tau yz, tau zy, tau yx, tau zx. But from the complementary shear stresses, we got complementary shear stress. That means this one. We say it is also as complementary shear stress. For the statement 2, जो two stress values थे, stresses on adjacent faces, the shear stress on the two adjacent faces, we call them as complementary shear stresses. But from the complementary shear stresses, we got tau xy equals tau yx. We got this one equals to this one. This one equals to this one. And this one equals to this one. So your matrix is kind of, can you guess? This way. If it is A, if it is B, if it is C, the value of A is also here, the value of B is also here, the value of C is also here. And here is your sigma x, sigma y, sigma z. So your matrix is symmetric about main diagonal. Okay. So this all we have studied, it was for the isotropic and homogeneous material. Then that is where the Hooke's law is valid. Isotropic homogeneous material. So for three-dimensional element, we have 9 stress components. But out of that, only 6 are independent. 6 components are independent. It implies you have to define 6 stress. You have to calculate 6 stress elements in order to define state of stress of that element. किसी particular element of the body को represent करने के लिए, present करने के लिए, उसको define करने के लिए आपको 6 stress components find करने होंगे. This one, and these 3. But for our study, we do talk about 2D. 2D के लिए आपका you have to only focus on sigma x, sigma y, tau xy, tau yx. Only focus on these 4 values. You have 4 components. but out of these only 3 you have to calculate. 3 are independent components. That's your sigma x, sigma z, sigma y, and tau xy. Okay. The main topic now is your stress strain curve. Stress strain curve. If you take a prismatic bar, that is prismatic bar मतलब कि it is a bar in which cross section does not vary over the length. अगर यहाँ पे cross sectional area A है यहाँ पे भी A होगा, A, and here is also A. That is your prismatic bar throughout the length L, but of different lengths. Suppose एक में आपने लिया L1 and different areas A1, and second one bar you take as L2, A2. Then you apply the load. इस पे आपने apply किया ऐसे. Suppose you applied a tensile strength test in the UTM universal testing machine. You applied force. Now there would be some deformation delta L also. So accordingly you would plot the graph for load deformation, load versus deformation. You would plot the graph of load deformation. Now what would happen for different values of these length and L. Suppose this one is your first जो आपका member था उसमें आपकी length L1 था and area A1, and in the second section specimen you take L2 as equals to L, but you varied the area to A2, that's equal to twice A1. Let's say suppose आपने area change किया to twice the area of first member. Now you know the deformation value of deformation is equal to PL upon AE. Now for the delta 1 you have load 1. Suppose you're applying load 1, P1, load is same, take load same, P L1 A1 is your A1, E1 is your fixed. It is a property of material. For the same material, we say both are of steel, E is also same. For the delta 2 you have P L1 upon twice A1 into E. So you can see suppose now if you divide it P by delta 1, you would get A1 E upon L1, and for the P by delta 2 you would get A twice A1 E upon L1. So you have what is this P by delta? Perpendicular by base. You got the slope tangent, that is the slope of the curve. You got one slope for one specimen and one slope, different slope for different specimen, second specimen. For the first specimen you have the value of slope equals to A1 E upon L. Let's say it is a constant K. It's a constant K. You got a slope of equals to K in the first specimen. Phi, say tan phi equals to phi. We say tan phi equals to phi. Tan phi 1 equals to K. But for For the second specimen, you got the tan phi 2 equals to twice k, 2 times k. उसका slope अलग निकला. For the same material, you are getting two different slopes of the curve. Twice k2, k1. It was k1. So if you study the stress strain curve by why stress strain curve? Why not a load deformation curve? Do you got the concept? Stress strain curve. Why will be using stress strain curve, not the load deformation curve? So for the different load deformation curves, your value of slope is varying, slope is changing. How to fix it? Now you have stress is equals to P by A. For the first cross section, you have stress equals to P by A1. So your sigma 1 equals to P by A1. And for your member 2, your cross sectional area is twice A1. For your sigma 2, you have P by twice A1. Now you have studied this. You have this equation, delta equals PL upon AE. We know delta equals stress. P by A is your stress, L by E, and delta by L is your what you call as strain. Delta by L is your strain, and sigma by E. So if you plot the graph of stress by strain, you will get the value of E. So for the first one, let's solve for the first one. For your sigma 1 equals P by A. As you can see here, as you can see from this derivation, that it doesn't depend on the area here. So if you check for the now you got this equation. If you plot the stress strain curve now for the same load deformation curve, if you derive from that stress strain curve, what you can get is like stress 1 by E1 equals to E, and stress 2 by E2 is equals to E. Okay. Stress 1 is equals to P by A1, and stress 2 is your P by twice A1. So your stress 1, let's say stress 1 is your sum. Let's take it as stress. We say stress 1 is your stress upon E. 1 equals E. But for the sigma 2 becomes just wait. So we can have this one you can remove. You have for sigma 1 you got strain 1, and for sigma 2 you got strain 2. That's equal to E. So your slope is fixed. That is if you plot the sigma versus strain curve, sigma strain curve, you got only one slope. That is tan phi is equals to E. That is E is fixed now. But in the first case, when you have low deformation curve, you are getting different values of E, different values of slope, as you can have here. Twice A1 to AE by L and AE by L, but you got here twice. So it was varying. slope was varying. But in the stress strain curve, you have the slope is fixed. From the Hooke's law, you have stress equals to constant into strain. That's how it has been derived using this concept. Okay. Now after the testing of the specimen in the universal testing machine, that is, you have solved for the compression test. Sorry, you have the specimen, you applied tensile force on this, and you check it for these deformations. You got strain, and you have P by A equals stress for different values of strains and different values of stresses. You plot the graph, stress strain curve. Then for the mild steel, you have mild steel. If we study the graph we got from the testing, it is somewhat like this. Initially, the stress strain curve is linear up to point A, then it kind of deflects to point B, then it goes like this. Sorry, it goes like this, and coming back. Then there is some sort of straight region, plateau. Then it's like this. It's your stress at this point, the maximum. It is your ultimate sigma ultimate strength of the specimen, and this one at point we can write as point D, point B, point A. This is your C, this is your origin, this is your D, this is your E, F, and G. Here is your sigma yield. We write it as yield strength. We say it is a yield strength of the material. It's around at B, or we can say it's at D. They are very close. B and D are very close in stress. Here the value of strain is 0.12%. 0.12%. The value of strain is here around 1.8%. The value of strain is here 10 to 15%. The value of strain here is 20 to 30%. 20 to 30%. Okay. Now we have to make another page. Sort of that. Let's copy it first. Wait for some time, guys. you are having this stress strain curve as this way. This was your initial position, then it got like this and come back, then it was like this, then this way. यहाँ पे आपका maximum पे आपका strain था 20 to 30% strain, and it was your stress, sigma ultimate, sigma yield at this point, D, E, F, A, B, C, and D, O. The OA, we say it is a linear curve, and A is your proportional limit, and B is your we say it's a B is your elastic limit, and C is your upper yield point, D is your lower yield point. E is your D to E is your plastic region, and after that you have F. F is your point where ultimate strength is reached, ultimate stress point. F is your E, F, G. G is your point where fracture occurs, fracture of the specimen occurs, fracture point. The region FG, we say it is as necking region. So in the OA we have linear curve. जो आपका Hooke's law है, that's valid in this region only, in the OA, where stress is proportional to strain. You write it like this: in the region OA, stress is proportional to strain, Hooke's law is valid. Here the strain is 0.12%. What does 0.12% means? जो आपका पूरा sum जो है, that's based on that Hooke's law. जो आपका material है उसमें stress is proportional to strain. That means उस point पे जो strain value है, that's very small. Very small. At point D you have 0.12%. 0.12% मतलब कि यार wait for some time, guys. Point 0.12%. 0.12% का मतलब है it is a strain which implies delta L upon L. Let's say you have a specimen of length 100 mm. At the point D आपका जो deformation, जो elongation है, that is equals to 0.12% into L. L is your 100. That means 0.12 mm. That means final length at D is equals to 100.12. That's almost equals to 100 mm. That means the overall strength of material is 0.1 mm. If you have a length L 100 mm, अगर आपका लेंथ, आपका जो भी आपका मेंबर है उसका अगर डायमेंशन 100 mm है, तो strength of material, it is up to the point where the material is deformed to 100.1 mm. My total deformation is 0.1 mm. That's very, very small. Now if you see from the graph, we seen from the graph, like at the ultimate stage, that is at the fracture point G, your maximum strain, that is 20 to 30%. 20 to 30% strain. That means अगर आपका member 100 mm था, at the failure point, time of failure, जो आपका deformation होगा, final length is equals to 130 mm, 120 to 130 mm. That means it has been deformed from 20 to 30 mm. But this large amount of deformation, we study it in plastic analysis in design of steel structures. Okay, for now we have strength of material, we only focus on this 0.1 mm, जो आपका छोटा सा 0.1 mm है. This is all strength of material and structural analysis. All the stuff, crazy stuff in this strength of material and structural analysis is just 0.11 mm of length 100 mm bar or specimen. Okay, so OA was your linear portion, and now you can now compare these values. A, B, C, D are very, very, very close. You can see these are very, very close in terms of strain. So for design purpose, we assume A, B, C, D to be same. That means we can use Hooke's law up to point D. This is your assumption. It doesn't affect so much. Now coming back to these critical points of the curve. A was your proportional limit up to which stress is proportional to strain. After that, stress is not proportional to strain. Then B is your elastic limit. What does elastic limit means? That means if load was such that the stresses created was, if the stress was below point B, there won't be any permanent deformation. That means आपने load बढ़ाया, आपका stress बढ़ा till point B. Now if you unload before B, suppose आपने जब specimen था उसको unload किया before B, what would happen? The body would come back elastically to its original position. जो इसका जो coming back position path जो होगा, that's the same in which it has moved to the point B. That's your reloading path. But if the load was such that the stress became greater than sigma B, this point B, it has crossed the point B. So after that, let's say you unloaded somewhere here. Now it won't come to its original position. It won't come from the position, from the path it followed during loading. It follows a different path. That path we draw it in a way such that the slope here is E and the slope here is also E. We draw a line parallel to the this proportional linear part of the curve, like this. We say it is this and this is parallel, and it will come back to it would come in this path after unloading. So elastic limit is the limit up to which stress there is permanent deformation. If the load is such that the stress exceeds the point stress B, then there is a plastic deformation of the body. Okay, now then you have upper yield point and lower yield point. We have here only one yield strength. That is the characteristics of the material. Say mild steel, उसका जो yield strength है, that is 250 megapascal. That's a fixed quantity. But you got two yield points in the mild steel. Why do we study mild steel? Firstly, mild steel को study इसलिए करते हैं क्योंकि mild steel got more number of points, more number of critical points to study or to do research than any other steel. Steel ही क्यों use करते हैं? Because we use steel everywhere in civil engineering, concrete and steel. So सबसे ज़्यादा points जो critical points that can be seen in the graph, that are observed only in mild steel. That's why we study mild steel. At point C, there is we say at point C we have at point C and point D. The point C is relatively variable. We say it's point C varies. It depends on the rate of loading. Loading rate पे depend करता है, rate of loading. Actually, there is a slippage of carbon atoms if we study the atomic structure. You have iron atoms, then there is a dislocation then you have a dislocation of the atoms. Here we say it is a dislocation is the locus of all defects. Then the carbon, you might have studied that those defects in your chemistry. We say carbon atoms are also present in the iron lattice. Carbon atoms. Suppose ये आपका carbon atoms है. They try to move to a point where the dislocation is maximum. The dislocation is maximum here, so they kind of overlap on this part that form a atmosphere that is called as coronal atmosphere. उसकी वजह से फिर क्या होता है कि there is more stress is needed to break that coronal atmosphere. Coronal atmosphere को break करने के लिए आपको more stress चाहिए. इसीलिए आपका जो point C है that rises. C point इसलिए आपका relatively ऊपर जाता है. उसके बाद once the coronal atmosphere is broken, then your stress decreases, and after that yield region starts to grow. This one. After B, you got C. C is because of the dislocations. Because of the dislocation affected that the coronal atmosphere created, you have to break that coronal atmosphere. For that, more stress is needed. Once that coronal atmosphere is broken, then the stress needed is less. Then you got the point D. Point D is your lower yield point. Lower yield point is a stable point. Lower yield point D is your stable point. It is stable. So we can say it is a characteristic of material. It is a characteristic of material. Material पे depend करता है. So your D does not vary with loading extra. So your lower yield point is stable, so it's your characteristic of the material. After that, this DE region, that is the plastic region. There's for small stress, or you can say no change in stress, there is large amount of deformation. More strain, देखो यहाँ पे आपका strain 1.8%, मतलब 1.8 mm आपका member elongate हो गया. If it was 100 mm initially, that means more deformation has occurred for a constant stress. This is your yield. This is your plastic region. The reason is like slippage of those carbon atoms in around that dislocation. We say that is the reason. So we don't care about the reason. We focus on the material itself, how the material properties are. Then we have the this region, EF region. EF region is your where is EF region? I forgot to write. EF region. EF region is your strain hardening region. Strain hardening region. The region, it is the region where it's only possible for a material if the material is ductile. That means if it undergoes large plastic deformation, that is plastic region, उसके बाद ही आपका strain hardening develop होता है. You can't find strain hardening in brittle material. No strain hardening. Strain hardening is only possible for ductile materials when they have undergone large plastic deformation. Large plastic deformation. इसका crystalline structure जो है, mild steel का जो crystalline structure है, that gets modified. Then it takes more stress, more and more stress for strain. To increase the strain, you have to increase the more and more stress. ठीक है. After that, you have point F. Point F is the point. It is the ultimate strength point. It is a point after which the diameter of the specimen gets reduced. Your FG region, we say in the FG region, your specimen was this one, like this one. Its area was initially A0. Then the new area will be lesser than initial area. So with strain, increase in strain, your area is getting decreased. So your stress is also getting decreased. This region is your necking region. Stress decreases because of local instability. And the final point is your point G. Point G, where the rupture of the material occurs. Rupture or failure of the material occurs. It occurs in a fashion of cup and cone failure. We say it is a cup and cone failure. Let's say you have this material like this. It's like this one. And this one is like this. cup and cone failure. The failure the failure angle is like it's 45 degrees. Okay, it makes 45 degrees with the horizontal, with the say this one, it is your 45 degrees, this one is your 45 degrees angle. The reason for that we will study in the further topic, that is your stress transformation. After that you can understand why 45 degrees your critical condition, at which why not 46, why not 44, 45 पे ही आपका fail करेगा ये material. We would study it why there. So this was all from the stress strain curve. This was a crazy topic. We had now erasing all that stuff. The page one also. Now coming back to the coming back for the mild stress. If we have same specimen mild steel, but you perform compression test. अभी तक आपने इस स्पेसिमेन पे टेंसाइल फोर्स अप्लाई किया था. नाउ यू अप्लाई compressive test, compressive force, sorry, apply force. So your graph looks like this way. Initially आपका straight जाएगा, then kind of goes like this. There is no part that is necking region is not here. This necking region is not there. Necking region इसमें है ही नहीं. Necking region not. No necking region in the compression test. It's a very important point. Why necking region is not? Because you are applying compressive force. The area is not getting reduced. There is some sort of bulging. Your material is kind of getting bulged. So how can necking be created? It's getting like this drum kind of thing. So there is we can say area is getting increased. How can necking occur? No necking. Your stress strain curve looks like this. Okay. And the slope here in the EC, we say modulus of elasticity of steel, the slope of curve of mild steel in compression is equals to E that you got from the tensile test. If you simultaneously plot both compression and tensile tests of the mild steel, those can be shown here like this way. Sorry. Then you got something like that, then you got this way, and here just like this. Here the slope is same. E in compression is equals to E in tension. Stress strain curve. ये आपका compression है, this is your tension. Okay. Now if you compare the stress strain curves of other materials, you have, if you plot different curves, let's say this one, then go like this one, then go like this. Sorry. So with increasing the carbon content. If you increase carbon content, if you increase the carbon content in the steel, your brittleness increase, but your elastic strain or elasticity decrease, or plus this uh, ductility, we can say, ductility decreases. This statement is frequently asked in exams. Ductility decreases. Like if you are having mild steel is a low carbon steel. Then you have medium carbon steel, medium carbon steel. Then you have high carbon steel, that's also called as structural steel. Okay, so here the slope for the each material is same. Modulus of elasticity is same for each of those steel specimens. But what is changing is the maximum stress and your strain range. Ductility decreases with increase of carbon content. As the carbon content increases, ductility decreases. Okay. Now some materials you have from this graph also, you can have this one. Last one is your structural steel. The curve is like this one. There's no kind of upper yield point and lower yield point. And if your materials also like aluminum, copper, and structural steel, they don't have a definite yield point. The stress strain curve is somewhat like this. Okay, here is some strain, say 20 to 25%. Strain is not here important. Now, how can you define the yield strength? Yield strength is a characteristic of material. So when we say some steel, we say how much is your yield strength. But for these materials, there is no definite yield strength. How do you calculate the yield strength for this material? We say you have a strain. We say you increase the load till you got a stress value, you got a strain value of, say, you increase the load till you got a stress value, increase the stress, that is increase the load, and till you got a strain value of 0.12%. 0.12%. No, 0.2%, sorry. 0.2%. 0.2% strain पे of stop करो. Then you make a line parallel to the initial part of the curve. This is parallel to this one. Then the slope here tan theta equals to slope here tan theta. The point where it cuts the curve, that we represent it as the yield stress or yield strength of the material. So the sigma yield, we also call it as proof stress. We also call it as proof stress. So a line parallel to the initial stress strain portion of the curve is we plot such that it's parallel to the initial portion. Okay, and at a point of 0.2% strain, we this curve is plotted, and the point where it touches this curve, stress strain curve, we mark it as the yield stress or proof stress or 0.2% stress. Okay, right one. This is your approximate value. Like modulus of elasticity of aluminum is 1/3 of modulus of elasticity of steel. We sometimes use it. We can use it in some questions also. So we can say that the 0.2% that the 0.2% proof stress is not a material property. It's only used for calculation purposes. Let's take one question on this curve. Write one question, important. Let's see, you have question number 1 of all the topics we have studied. You have an alloy, its stress strain curve relation, stress strain curve relation is y equals ax square plus bx, where y is stress in Newton per mm square and x is your strain value. The value of A is equal to minus 7727.36 megapascal. This Newton per mm square is also a megapascal, we say it as megapascal, and value of B is 9276.6 megapascal. The question is, find the yield stress of alloy using 0.2% proof stress. So you have a curve. It's like this. The equation is y equals ax square. Y equals ax square plus bx. How can you solve this question from the study we have shown? I have shown you here. This is your equation, quadratic equation or parabolic equation for the variation of stress strain. And for the yield stress, you need to check the you need to draw a line whose slope is also equals to the stress strain curve slope, okay, at 0.2% strain. So initially we need to find the slope of the curve. If we get the slope of the curve, then we will say what is the next step. Let's solve for the slope of the curve. Slope dy by dx, you differentiate it, you get 2ax plus b. Now this is your y and this is your x. If you use boundary condition, you say at x is equal to 0. At x equals 0, that means at origin you have a slope of, you got a e equals to, don't write e as like, say you have a slope of dy by dx equals to 2 into a into 0 plus b. You got a slope of b that's equals to 9276.6 MPa. We know same slope would be for the line parallel to the initial portion of the curve at 0.2%. strain. If you draw a tangent to the curve, initial part of the curve, it would be somewhat like this. You got the value of b here and here. The value of b is also same. Now you have a straight line here. You have a straight line here. Y equals mx plus c. See, it's intercept. We don't know what is the value of c for this straight line. It might be something we want to check. We know y equals mx plus c. What is the value of m? Slope, value of slope is equals to b x plus c. Okay. Now if we apply boundary conditions, we can say at b equals at we want to check the value of c intercept. How can we get the value of c? If we apply boundary condition, say at y equals 0, you got c, you got c equals minus b x. Okay. Okay. So c equals minus b. What's your b? 9276.6 MPa into x. Now we know x. Do you know x? Yeah, of course we do know x. The x is value is 0.2% strain, 0.2%. If we calculate this, minus 9276.6 into x, 0.2% strain, 0.2%. You got value of c. Value of c comes out to be minus 18.5532 megapascal. Now you got two equations, y equals ax squared plus bx, and you got equation y equals bx plus c. Now what you want from the equation, you want to check the point, you want to check the, you have two equations. One is your parabolic equation, and one is your straight line equation. We want to check the value of sigma y here, but for that, if you intersected these, we want to check where is the intersection point. We want to check the value of x. If we get the value of x, then in any of one of the equations we can get the value of y. That is your sigma y. Understand? Yeah. Let's combine these two equations. You have y equals ax squared plus bx. Your y was equals to 9276.6. No, your a was equals to, can have here a is equals to 7727.36 minus 7727.36 x square plus bx. B was your 9276.6x. If we equate it with the value of bx plus c, b was your 9276.6 x plus c. C, what is the value of c? C was your minus 18.5532. Okay. When you calculate this quadratic equation, you get the value of x equals to 0.049. That's the strain value of 4.9% strain level. So add the value of 4.9 strain percent. So we know that the stress, yield stress, is calculated at 0.2% proof stress. But the point, these intersection of these two lines, we got the value of x as 4.9%. So at that point, the value of y will give you yield stress. So point using x is equal to this value in any of these two equations. Y equals, let's take in equation y equals ax square plus b minus 77 minus 77, this one, minus 77 to 7.36 into x square 4.9%, this x square plus bx 9276.6 into x 0.049. You got the value of stress, that's your yield stress, sigma y equals to 436 megapascal. Got it? Okay. Now we have, if we have the concept, the next one, you have wait, something missing. You have stress strain curve for brittle material. Like, for example, you have cast iron. This is your brittle material. In this point, in this curve, you got stress strain curve like this. There is no in this curve. There is no necking, and this is your failure point, sigma failure. At this point, your material fails, and the value of strain is very small. And value of strain is very small. Strain is very small at failure. However, in the ductile material, there was very large amount of plastic deformation. There was 20 to 30% plastic deformation. But in the brittle material, it suddenly fails. There's no necking. Strains are very small. Okay. And the failure, if we applied tensile force P, and the failure was somewhat like this one. But in the mild steel, the failure was somewhat cup and cone failure. This one. The reasons we will be learning in other topics. Okay. Now, our topic: true stress and true strain. True stress and true strain. अभी तक जो हम पढ़ रहे थे, that was engineering strain and engineering stress. Now we will study true stress and true strain. Actually, this was your sample specimen. Its cross-sectional area was A0 initially. You applied force P, length was L. Finally, the deformations would be after the application of loads. There will be final length will be L plus delta L, and to maintain your volume, the area final would be lesser than area cross-section. The cross-sectional area at the final stage will be lesser than as compared to initial area. So if we say what's engineering strain, अभी तक जो हम पढ़ रहे थे, हम बोल रहे थे sigma equals P by A. We at every point when we plotted the stress strain curve, we fixed the area to A0. We said that the area we fixed, only the load we varied, and the stress we got it was engineering strain, engineering stress. But the true stress, sigma true, is load upon true area. true area is your final area. It is lesser than a naught. So for intention, we can write it. Intention testing, your final area, a final, or we can write a area at any time t is lesser than initial area. So if it is lesser, that means true stress is greater than sigma. So if you plot the graph, you are having stress strain curve. This was your engineering stress strain curve. But for the true stress strain curve, after the yielding, the graph looks like this way. It is more. The stress values are more. Sigma, we can write it as true stress strain curve. True stress strain curve. So you are at ultimate stage, you have a difference. Can you see? At ultimate strength, true strength is more. True stress strain curve is more. But for in the true stress strain curve, there is a problem, like at every stage you have to get the value of A, but it's very difficult in testing. You can't find the value of A, that's varying with time. So for simplified analysis, we say don't take it as variable area, take it as fixed. So we have engineering stress. Sounds great. Now you have in the tension. No, in the compression. In compression. Now you have same specimen. Apply compressive force P. Initially the area was A naught, length was L. Now final length would be L minus delta L, and the area A would be greater than A naught, isn't it? If length decreases, area would increase, so that volume is constant. Okay. So your engineering stress, that's P by A naught. Now true stress is equals to P upon cross-sectional area at any time after the application of load. Say the area is greater than A naught. A greater than A naught. So your stress will be lesser than sigma. That's lesser than sigma. So if you plot the stress strain curve in compression, what's the nature? So it was here like this and like this. Here the slope is same. You get somewhat like this. This was your engineering stress strain curve. But we have seen that the true stress decreases than true strain. So after that point, yield the point, you say the stress is getting decreased. So it's your true stress strain curve. These are like objective questions that can be asked in engineering service examination, ESE. Okay. So what is your true strain? If you solve the true strain, let's say your true strain, you have engineering strain was epsilon equals delta L upon L. Initially was L naught, take it as L naught, but after some time if we calculate the true strain is change in length upon upon that particular point. Between the two increments of loads, say from P1 to P2, your length was L and it became L plus delta L. But L and L naught are not the same. We say after some time t. So there is small displacement at small increment of load. Okay, so engineering strain would be calculated, say if we calculate it mathematically, we would say engineering strain. Now true strain for increment of loading, for finite increment of loading, such that length changes from, say, initial L naught to any length L. You can say true strain is integral dl upon L from L naught to L. This is your ln L by L naught. Write it. L is at any time t, L naught is your initial length of specimen. L is at any stage. Okay. So we want to check the relation between true stress and engineering stress relation. Sigma engineering and sigma true stress and true engineering stress relation. In tension, your length increases because delta L, you are extending the material. So volume conservation says initial area and initial length equals area at any time d and length at any time d. So your area at any time d equals A naught L naught upon L. Since in tension, L at any time t is L naught plus delta L. So we can write it A naught L naught L naught plus delta L. So we can have A naught divided by, we can divide it here, L naught plus delta L upon L naught. What we can get, we'll say A naught upon 1 plus delta L upon L naught. That's your delta L upon L naught is your engineering strain. Change in length upon original length. That's your that we can say it is what it is, engineering strain. So your area at any time t equals A naught upon 1 plus E. But what's the value of stress? Stress is equals P by A. So your engineering stress is P by A naught and your true stress is P by A. So if you use the value of P here, we get P equals sigma into A naught. Sigma A naught upon A. Sigma A naught upon A. What is the value of A we got? That's equals to this one. A naught we got in a value of area at any time t equals A naught upon 1 plus epsilon. So your true strain is equivalent to engineering strain into 1 plus engineering strain. 1 plus epsilon. Okay. Similarly, for the compression, you can get true strain equals to engineering stress. True stress equals to engineering stress 1 minus epsilon. Because the length is getting decreased, accordingly you get this relation. Let's solve one question. Like it's a simple question. It's saying like the volume of tensile specimen is constant while plastic deformation occurs. It says if the initial diameter of the specimen is d1, like in the UTM universal testing machine, you applied tensile test. I said tensile test of specimen. Okay, uh, the initial diameter of the specimen is d1. D1 is the initial diameter. And when the diameter is d, when dia changes to d, say at any time d after loading, now diameter is d, show that true strain equals to ln 2 times ln d1 by d. That's initial diameter by diameter at any time t. If the volume is constant, say we have volume constant, we can say volume equals pi by 4 d1 square. Initial diameter is d1. The length, initial length would be L naught. Say initial length is L naught. That is equals to pi by 4 diameter at any time d square into length would be different. That would be more than the initial length L naught. So if we have to derive this result. This result we have to derive. By the way, what is the value of true strain? We have calculated that value of true strain earlier somewhere. Yeah, this one. True strain equals integral ln L by L naught. True strain equals ln L by L naught. Okay. We know that. Okay. True strain is equals to ln L by L naught. So if you simplify this equation in terms of L by L naught, you would get d square by d1 square. Applying here ln L by L naught equals to ln d by d1 square. So your ln L by L naught is equals to true strain. That means true strain is equals to 2 times ln d by d1. Okay. From the results we got earlier, we say true stress is equals to true stress is equals to engineering stress 1 plus epsilon for tension test in tension. Similarly, if you want to solve, if you're going to get the result of true strain in terms of engineering strain, we would say 1 plus epsilon. Does it make sense? No, it's very wrong, bro. Not. We have to check now relation true strain and engineering strain. Relation. We have to show the relation is like epsilon true equals ln 1 plus epsilon. We know true strain equals ln length at any time t by initial length. In tension test, L is greater than L naught. So your ln L plus delta L by L naught. Oh, L naught plus delta L by L naught. Is it okay? Initially आपका length L naught था. So your length at any time t equals L naught plus delta L. It becomes L naught ln 1 plus epsilon. Delta L by L naught is your engineering strain. So your true strain equals ln 1 plus epsilon. Now write the properties of materials. Next topic, properties of materials. First one is your elasticity. We earlier studied elastic limit. That's the point B. Initially it was slope was linear, then it shifts like this. It was your B. We say up to this point, if stress was below this point and you unload, that means you remove the loading, the path followed would be same. Path would be same follower. Same path would be follower. But after that, if you did not follow this thing, if you say no, after B, say this is your B, after B I want to add more and more loads, that means more stress. Then after that, if you unload, after that you unload that means at this stage you unload that specimen. जो भी आपका specimen था उसको आपने unload किया, then a part of strain, this is your total strain at this point, at this value of strain. Okay, some part of it would follow a path such that the slope of that path would be parallel to the initial portion of that curve. So this is parallel to this. So ये वाले path आपका follow करेगा. After the elastic limit, the path followed is this one, that's parallel to the initial portion of the stress strain curve. So we can then conclude that the part here, this part, it has become permanent. It can't restore this part, so it has become plastic region, plastic strain, and this one is elastic strain. Plastic strain means it has recovered this part and it's unable to recover this part. That means it has become permanent. Deformation has occurred. Permanent deformation has occurred. Here we can say it's unloading. Okay, next one is your plasticity. We can say the property by which material undergoes inelastic strain. That means it is not a recoverable strain. After the elastic limit, the strain was recoverable. That means it can come back to its original position. But after that, you have this plastic region. If somewhere here you have this strain, you can't recover all of this strain. Out of this total area, only a part of area, if you unload somewhere, a part of it is getting plastic and some part is elastic, say on reloading. That means the property by which material undergoes inelastic strain. Your plastic strain is inelastic strain, it's not elastic strain. Okay. Ductility. What do you mean by ductility? Next one, ductility. You have graph here. ऐसे कुछ जाता है ऐसे. So at this point, strain was 0.12%. At this point, it was 1.8% strain. We say if the post-elastic strain, here is elastic limit. If post-elastic strain is greater than 5%, then material is ductile. ductile material की property है, a post elastic strain is greater than 5%. But you have seen in the mild steel, the maximum strain it was going to 20 to 30%. It's just saying if it's 5%, okay, we can say it is ductile. So your mild steel is very ductile. Mild steel is ductile. Okay. In the ductile material, you have yield strength in compression greater than or equal to yield strength in tension greater than or equal to tau. That means strength of the ductile material is critical in shear. That means the materials which are ductile fail in shear stress, not in this normal stress, tensile stress, compressive stress. No, they are good in those two. They have a good strength in tension or compression, but in the shear they fail. Ductile materials fail in shear. Ductile materials that is failing in shear. We have seen cup and cone failure. It's because material is ductile and material is itself weak in shear, so you are having a cup and cone failure. Okay, next one is your, can you guess? Brittleness. So brittleness is like post elastic strain less than 5%. In this, you have the critical strength is tension, tensile strength, sigma YT. Tensile strength is critical. That means materials which are brittle, they fail in tension. So your cast iron was brittle, the specimen was failing in normal to the direction of applied tensile force. One thing is there, I forgot initially. You have a beam, you apply force P, say it is tensile. Because of that, strains get developed, you got L plus delta L. So the flow is like this. What is stress strain? You mean, how can you say the path? We can say आपका tensile force है, it will give you tensile strain, and tensile strain develop हुआ तो you have tensile stress developed. So this is your path. So if question is arising, which one is coming first, stress or strain? You would say the load, say the load is tensile, it would cause tensile strain, and because of tensile strain, stress is getting developed. Okay. Next property, that's your malleability. You know, you might have studied that ability to deform into sheets. In the ductility, you have wire, you stretch it till it becomes a thin wire like this one. So its application is in wires. But in malleability, and you apply here tensile force. Okay, in the malleability, you deform the material into sheets. How do you deform the material into sheets? Say it was a material here. When you apply some force, compressive force, say by hammering action, material will spread laterally, and the material will become like a plate. Sheets. So malleability is a property to deform into sheets under the application of compressive forces. The next one is your creep. In the beginning of this lecture, we said that the solid mechanics, we have the body, applied force, and the displacement at different time intervals was constant. Deformations don't vary with time. Deflections, deformations don't vary with time. But what's the creep concept? Creep says, if you have a concrete, for example, for the concrete case, want to check what's the creep. The graph is like time and strain. You have here strain. Initially, when you apply the load, suppose it is a beam, or there are two poles. You can say these are two poles, and this is a wire between the two poles, electric poles, and this is a wire. Okay, or anything beam between two supports. Anything you can imagine. Say the loads are there, P loading are there. These are fixed under sustained load. Load is not varying. Under sustained load, we want to check the effect. There would be instantaneous displacement. So there would be instantaneous strain, sigma instantaneous strain. Then after that, strain increases with time. Then it becomes constant. Now, after some time, if you reload the beam or that wire between the electric poles, say if you unload the say the beam, concrete beam, it would follow the paths, like it would undergo we call it as instantaneous elastic recovery. It has recovered elastically this part. Then after that, with time, it would regain some more part, but with time. We can say it time varying recovery. But the end, you can see this part is unrecoverable. This is, we can say, it is a residual strain developed. This strain is developed because of this creep. So creep, it is an additional strain. It is an additional strain developed in the material, say any specimen, body, element, member, beam, wire. Additional strain developed under static load, under sustained load, or the load is fixed. Sustained means load is fixed. Under sustained load, within elastic limit. The load is within the elastic limit itself, but still there is extra deformation occurring because of this creep. If you have stress strain curve, it is somewhat similar to that of stress strain curve in the plastic range. If you have this curve, this one, then you have this. At constant stress, we have plastic deformation of this part, but it was in the plastic range. But it's saying that the load is under the elastic limit. Load is within the elastic limit, but still there is an additional strain developed with time. So that is because of the effect of creep. So you have in the concrete, you have to ensure creep effects are minimized. If we make a general diagram for the materials for the creep, other materials for the creep, we can show it like this one. Say here is the instantaneous deformation, instantaneous strain. Then after that, it goes like this way. Then you at any instant you unload, it will become elastic recovery, instantaneous elastic recovery. Then with time varying recovery, there will be some time varying recovery. Then after that, this is your permanent strain. This is for general case, general, say steel, general steel, strain stress. Now time, with time आपका strain vary हो रहा है. Here is unloading. Okay. Now the strain, the creep is a function of, creep effect is predominant in higher temperatures. If temperature is high, next one is your stress level, how much stress is, stress, time, type of loading, whether loading is static or dynamic. So these are the factors on which stress, these creep strain depends on. So creep is more important more critical at higher temperatures and higher stresses. Rest we can say, let's ignore the creep strain. And we can conclude from the graph also that the creep strain is not 100% recoverable, isn't it? There is a permanent strain developed because of creep, so it's not 100% recoverable. Now because of the creep, suppose there were two poles, electric poles, the wire was between them, under some force was applied, initial force was there, P, some P. Okay. Under sustained load with time, your length, there is a sagging, you can say. After some time when you visited the poles, there is some sort of sagging, so your length has increased. Because of that, the stresses in the wire reduce. Stress in the wire reduces. This is because of creep. So we call it this effect as relaxation of stress. Stress relaxation. So if we have a graph, we say after a stress naught value, then the graph, stress decreases, then it remains constant. That means after time t, when you check it, the wire at time t naught, you were having stress t naught, stress sigma naught, but after some time t, when you visited back, the stress has been decreased up to sigma t, but it remains constant after that. This loss of stress is because of creep. We call it as relaxation. The difference between these two, we call it as relaxation, stress relaxation. Now next property is your fatigue. Fatigue says you have a graph. It is for ferrous materials, say steel, ferrous materials. This is called as SN curve. Stress and number of cycles of loading, which cause fatigue failure. So there is we say the fatigue occurs in a material when the loading is repeated and cyclic. So you apply 10 tensile, then you apply after that 10 kilonewton compressive, then it goes repeated on and on and on. So materials go under fatigue. There is a repeated strain, progressive cracking develops So the material fails even before the elastic limit. You can say material flow, material the load at which material fails, the load at which material fails is lesser than the load it could have sustained statically. It sustained statically. मतलब अगर एक ही लोड आपका अप्लाई हुआ होता बॉडी पे से टेंसाइल फोर्स only tensile force was there, the stress strain curve was something like that, then the material with, if the load was within the elastic limit, the stress was this one, so material was not getting yielded or it was not getting ultimate yield strength. But if your material is using under prolonged these repeated cycles of stresses and repeated we can say reversal of stresses, so compression tension, then the material fails even before the elastic limit, then we call that as fatigue effect. There is if you draw a line here, you can say after some number of cycles, after some n number of cycles, where this n is infinite, here is infinite number of cycles, there is a limit sigma end. This is a limit, we call it as endurance limit. Sigma endurance. Say if the material is subjected to stresses lesser than this endurance limit, material would never undergo fatigue failure. Will not undergo fatigue failure. Even for the large infinite number of cycles also. If you do infinite number of these compression test, tension, compression test, and tension, reversal of stresses or repeated cyclic loadings, still the material would not undergo fatigue if the stress is below the endurance limit. For the structural steel, you have endurance limit approximately equals to sigma tensile strength ultimate divided by 2. Now the important two properties are coming. Now be ready for those two properties. Next property, that is your we call it as resilience. Resilience. Say you have a stress strain curve. You say this is your elastic limit, okay, point B. If we we say the resilience is the energy stored in the material up to elastic limit, or point B, and to have this energy recovered, and we recover that energy if at the time of reloading, we can say. So say spring example, application is in the springs of the vehicles, say your mountain bikes, say springs. What this means? The energy is stored in the material up to elastic limit. Say this is your elastic limit. The area of the stress strain curve up to elastic limit. This is a linear portion now. We know proportional limit up to that it is linear, and A and B are approximately equals, closer, very closer. We can say this is a triangle. The area is half sigma epsilon. So writing it in terms of stress and E, we say half of sigma, and your epsilon is from the Hooke's law, stress equals E epsilon. So epsilon is sigma by E, so it becomes this way, sigma squared by 2E. So there is a concept. This is, we also say it as proof resilience to be more accurate. Proof resilience. So next one is your modulus of resilience. Modulus of resilience. Modulus of resilience. It is the strain energy stored in the material that is equals to stress area of stress strain curve, up to elastic limit, that we have calculated half of sigma square by 2e, 1 by 2 sigma square by E. Now resilience, proof resilience is actually modulus of resilience into volume. When we say proof per unit volume, when we say resilience per unit volume, that is equals to modulus of resilience. So your specimen was like a cylindrical specimen of length L and diameter D. We say resilience is modulus of resilience, that is sigma squared by 2E into area pi by 4 D square into length L. This is your more proof resilience or resilience. In the springs of those bikes, you don't want the spring to be undergo elastic, this beyond the elastic limit. Say spring is like this one. If the pitch, say it is a pitch, if there is elastic, if there is plastic strain, if the plastic strain develops, the pitch gets changed, and then the configuration of the what you call as this spring also gets changed. We don't want the spring to go beyond elastic limit. That we want its function to be under the elastic limit, so that it can recover back after reloading. Say bike gets crashed or some sort of any stuff happens, so the energy that it's getting stored at the time of impact, it should be released or recovered again. That's only possible if the material is elastic. It is in the elastic region. If it goes beyond the elastic region, that's in the plastic region, it can't recover. It can't relieve that energy back. So this is the application. Next property, that's your toughness. Now this property we can use it in cars body parts for accidental loadings. Say there is an accident and car gets collided with some another car. So at that time, the body parts of the car are designed based on toughness. Say you have stress strain curve, you have this way, then goes like this and this. Say that this one is your G, fracture point. This area under the stress strain curve up to the fracture point. Area of stress strain curve up to fracture point. That equals to half of, that is approximately equals to half of sigma ultimate. This is your ultimate, this is your yield divided by 2 into strain at ultimate, strain at failure point. But we don't care about this part. We would say the area under the stress strain curve up to the fracture point. The total this is equals to total strain energy, total strain energy stored till fracture, that we also call as modulus of toughness. So if you say toughness is earlier, as we seen, modulus of toughness into volume. So from the two properties we saw here, these two, resilience and toughness, we say resilience and toughness are not the properties of material. These are not material properties, but modulus of resilience and modulus of toughness are the properties of material. These are the properties of material, because these two are not dimension dependent. Because we say modulus of toughness is area under the stress strain curve till fracture, and modulus of resilience is area under the stress strain curve up to the elastic limit. There is no concept of the material dimensions. So once there is no material dimension, so it only depends on the material property, that's elasticity, modulus of elasticity, bulk modulus of elasticity, E, that's in stress strain curve. Okay, next one is your tenacity. Okay, final property, that is tenacity. It is this property to resist a fracture under the action of tensile forces. So if your ultimate tensile strength is more, that means you are having property of tenacity. Okay. Now next we have topic approximate stress strain curves of materials. You have this one. You have different materials. Number one, take this one as, okay, say initially the path is like this, stress strain curve, then it goes like this. Another one is this one, another one is this one, another one is this way, another one goes this way, then this way. We say this one material, it is called as elasto and plastic material. This is stress strain curve, we call it as elasto plastic material. This one is your, there's no elastic region, so it is your ideal plastic, or we can say rigid ideal plastic, rigid plastic. There's no elastic region. For this one, there is even at zero stress, it has deformed. So we can say it is ideal fluid. It has a fluid behavior. Under no even zero stress, there is deformation, ideal fluid. And for this, even large number of stress, there is no deformation. So it is ideal rigid, as we have studied earlier that the rigid body concept. Even if we apply a huge amount of force, there is no deformation in the body strain. This was your ideal rigid. But it is an ideal. There's no concept actually any of ideal. Next one is your elastoplastic material, but with strain, with strain hardening. So this was all from the lecture. We have studied stress, strains, and properties of the material. Now, the next lecture will be going for the deformation of the bars, deformation of the material, the calculation of deflections, and stresses under the application of if the material is composite and the body and there is temperature application. So that is a practical application point of view. This was just a conceptual lecture part. Maybe it might have been boring. Okay, next one we would deal with in the next lecture. Okay.